Thank you, Chris. Thank you very much. Thank you, everyone, for making the time. I appreciate, being able to attend these presentations remotely and really valuable in today's world. Uh, Good morning to you in California. It's 6:30 my time, and hopefully it's afternoon, morning, whatever time zone you are in. Today's presentation is really focused on mechanistic pathways and tools for minimizing drug precipitation. But as we speak through it, we will take a broader look at what's happening in the solution formulations of small molecule drugs and also large molecule drugs. So let's start to move in. Three focus areas of CMC, the three key pillars of CMC are bioavailability, stability, and manufacturability, as all of us almost intuitively know and work towards. We look at the risks, we minimize the risks, we focus on specific risks such as stability, is there an impurity, or in terms of bioavailability, do we need to modulate exposure, or can we manufacture a dosage form at a scale? And all of these are really influenced by excipients and by the modulation that we do in the drug product. So in today's talk, what I would try to focus on is the role of excipients included, but really how do
Looking
they
at the phenomena of drug in solution introduced through a variety of means, including pH, for example, or co-solvents, or just the solubility of the molecule itself. There are phenomena that happen in solution we need to pay attention to, and these phenomena include aggregation, complexation, and self-association. We need to understand these phenomena at a molecular level and then understand macroscopically how they impact the formulation and the product that we are trying to make. And I would concede that these are the inevitable phenomena for weakly acidic and weakly basic drugs, primarily because these drugs tend to ionize and self-associate and interact with each other in addition to interacting with the solvent and other components of solution. There will be three examples or case studies which I will use to highlight this process. The first one, written in yellow on the left, is process-induced aggregation in a protein therapeutic. The second one, written in the bottom yellow box, drug-drug self-association, modeling, and in vivo relevance. And the third, as I say, on the right, drug excipient complexation, agglomeration, and in vivo relevance. Key messages that we will hear here and try to learn is biorelevance is a function of dose and fluid composition. And on the right, extent and strength of binding are the key parameters. If there is one take-home message that we want to take from this presentation, it is the importance of molecular interactions at the scale of molecules in solution and how they impact the large-scale phenomena.
So thinking about the dynamic interplays in solution, the key message that I think we want to take away from today's talk through different case studies is that the self-association shown on the right side is really a function of the drug itself, and it is influenced with the complexation behavior that is shown on the left side. And this complexation can happen with other species in solutions such as excipients. These phenomena can lead to supersaturation, shown on the top middle, or it could lead to precipitation. And these are important also in the performance and behavior. Now, essentially having surfactants, surfactants or polyionic species as excipients makes a difference. Amphiphilic species will lead from self-association to supersaturation, and that's what happens with lots of our drugs. And crystallization can also happen when self-association is the behavior in solution for given drugs. Now, we will have some case studies here, and those numbers are highlighted here for each of these. And these case studies really will highlight the importance of drug-drug interaction, drug-excipient interaction, and its role in either supersaturation or in precipitation of the drug. Now, thinking about role of self-association of macromolecules on solution properties. Now, this is a case of a large molecule compound. In this large molecule compound, you have, let's say, protein antibodies that form loose networks of association with each other in solution. And one of the big things we had observed was that when we prepare concentrated protein solutions using tangential film filtration or using centricon-based normal flow filtration, we observe a difference in behavior. And that difference in behavior is observed upon storage. The viscosity of the solution changes. And this change in viscosity, as you can see in the bottom top right graph, is more for thin film, for thin uh, tangential flow filtration prepared samples. And this was really linked to the interactions in solution as demonstrated on the bottom right. And those interactions leading to loose associations between proteins that in turn translates into the increase in viscosity of solutions. And that, as you can imagine, for a formulation that is supposed to be injected is highly undesirable. So in this case study of, this is the first case study, and in this case study of a protein sensitive to aggregation, as I mentioned, you would start to see viscosity change upon storage. Now, what is also happening with viscosity change is also change in the size. And this is the size of subvisible particles. And of course, we are concerned about the size of subvisible particles because these particles upon storage and they grow and they can actually lead to precipitation in those parenteral solutions, which is not desirable. To show you some of the data that we had seen, so top two plots are TFF process, tangential film filtration process for this protein, 50 milligrams per ml concentration on the left, 150 milligrams per ml on the right. And you can see those yellow bars increasing. And the yellow bars are indicative of high molecular weight species. On the other hand, the centricon process, the normal flow filtration process at 150 milligrams per ml bottom right, shows those yellow bars, which are pretty nascent. They are not increasing as much as the TFF process on the top right. So here is the difference that comes in the high molecular weight species and also in the viscosity of the formulation, depending on how you prepare it. And this was linked at a molecular level to the association between the proteins. And this association between the proteins is really driven by the hydrodynamics and also by the surface configuration of those proteins. Now, we had a hypothesis as this work was completed and published. We looked through what is determining the thermodynamics or energetics of protein aggregation. And this work is published, and this is from the literature, and it really highlights the thermodynamic minima for protein interaction with each other. And how is the concentration of one of the excipients, for example, sucrose, playing a role in this particular interaction. In our case, we had a similar behavior observation that when you have a centricon process, as shown in the top plots, at a higher temperature, yes, the protein does have propensity to form associations with each other. But when you have tangential flow filtration process, that propensity is higher. Those sustained long-range hydrophobic protein-protein interactions, they have higher propensity to form at using a process where protein surface is more exposed. Now, this is an example of self-association that leads to challenges for a protein formulation on storage. Now, I'll switch gears and I'll talk about self-association that can lead to supersaturation for small molecules. Now, this is an example of a small molecule compound where the drug self-associates, the drug associates with itself. And the data I'm showing here is the plasma concentration time profile of this drug in the clinic. So those black dots are the clinical data with the standard deviations as shown. And those dotted lines and the solid lines, they are the modeling and simulation of GastroPlus. And in this modeling and simulation, we have used precipitation times which are shown in the insert from 9 seconds all the way to 900,000 seconds, essentially trying to simulate a formulation that may not precipitate upon transition from gastric to the intestinal compartment versus a formulation that will precipitate rapidly. And what we are observing here is that in vivo profile is indicative that the formulation will not precipitate going from the gastric to the intestinal environment. And this is indicative of supersaturation, which is achieved in vivo, even though we do not have in vivo data or in vivo probes to measure that supersaturation. So essentially focusing on this second case study where self-association is helping with the supersaturation of a drug and making the absorption, oral absorption, more robust. Now, how can we start to study this? That same compound, when we study this in vitro, the probe we are using, the tool we are using is going from a pH of simulated gastric fluid to fasted state intestinal fluid. This pH shift, does it lead to rapid crashing of the drug? In many cases, we would see a rapid crashing. But in this particular case, what we see is that black line indicative of 200 milligram dose and the blue line indicative of 400 milligram dose, they pretty much maintain supersaturation. So the drug comes down, crashing down, but then it picks itself up and maintains pretty high concentration for a long period of time. 30 hours time window is much longer than the biorelevant time window of absorption, which could be in the insert, as you can see, about 5 hours. So this is indicative of the supersaturation. This is one of the in vitro assays that can be quickly used after the pH shift. We also talk about the supersaturation after pH shift in buffers and the parachute effect. So essentially, if you look at different degrees of supersaturation, 25, 12, or 9-fold supersaturation here, and time on the x-axis, are we able to maintain supersaturation and for how long? And you can see, depending on the degree of supersaturation, the fall of the parachute is different. So 25-fold comes down very rapidly, whereas 12 and 9-fold are able to maintain themselves for a prolonged period of time. And these are relevant to the in vivo behavior of the compound. Now, the self-association or self-assembly of molecules in solution is well known. It's not unique to one particular compound. Many compounds go through this process, and this is an example from literature. But how do we start to study, how do we start to understand that it's important and relevant to our compounds in development, especially in pharmaceutical development when we encounter a new compound? And this is the key tool that I would point your attention to, which you can use in your routine analysis to understand whether you are dealing with a compound that may have this issue. And this is the simple pH solubility profile that we generate for our portfolio compounds. And when you look at the pH solubility profile, the experimental data shown here with the closed triangles, that really highlights what is the solubility as a function of pH, whereas the theoretical is the Henderson-Hasselbalch prediction that we can easily make using the molecule properties. As you can see, there is a positive deviation from the Henderson-Hasselbalch prediction for the compound in this particular scenario, and it's a weak base compound, so solubility is going up at the acidic pH. This positive deviation is indicative of self-association. Of course, there are many other tools such as NMR proton shift. So shift in the protons as you increase the concentration, or you can look at the diffusion coefficient of the molecule as you increase the concentration as a function of concentration. You can also look at the surface tension. And again, these plots are showing a behavior that's more consistent with a self-associating compound rather than with a compound that has a sharp micellar shift. So instead of having a two-slope micelle kind of a behavior, this behavior is more consistent with continuous increase in the number of molecules getting self-associated. Particle size distribution again shows as a function of concentration. You can have different sizes of structures, which may not be true micelles, but they are actually structures that form in solution, the colloidal structures. And again, another very insightful tool, although it's labor intensive, is isothermal titration calorimetry. So as you increase the monomer concentration on the x-axis, the enthalpy of drug interaction on the y-axis shows a very continuous profile, which is different than a binary profile that you would see with the line that's indicated here. Again, indicative of a continuous mode of association. What's happening here in solution, right? So in this particular compound, And in this particular example, what you're seeing on the y-axis is the free energy, and on the x-axis is the um, change that's required when you do a pH shift from the acidic to the basic pH. So as you move from the acidic to the basic pH on the x-axis from left to right, you have self-associated species in solution with high free surface energy, and those species undergo into the basic solution another structural shift that leads to interaction and change in the ionization. But that does not take away the benefit of self-association to the crystalline form that's shown on the bottom right. So crystallization of a drug or precipitation of a drug at the basic pH, there is an enthalpic barrier, and that enthalpic barrier requires rearrangement of the molecules before it will actually precipitate. And that rearrangement is inhibited by the self-association of the drug itself. And this, we believe, is the underlying reason why supersaturation through self-association is beneficial to in vivo performance. In the next few minutes, I want to walk you through a couple of case studies where it can become, promoted with the excipients. So for example, this is a different compound here. And in this compound, we are talking about self-association, which actually is promoted with complexation with an excipient and how it impacts product performance. Product performance in this case will be the in vivo performance. So this compound, GDC-0152 solubility shown on the y-axis, pH on the x-axis, you see that behavior that we talked about, positive deviation from the Henderson-Hasselbalch equation. We know there is self-association of this compound. But what happens when we also include an excipient? So in the bottom left plot, we have succinic acid as an excipient on the x-axis. As a function of the concentration of succinic acid, the solubility of the compound increases. So the excipient is helping with the solubility essentially in a quite significant way when you keep the pH fixed at, I think this is about pH 5. Now, what also happens is when you have cyclodextrin, your solubility increases. But solubility increase with cyclodextrin is not as much as the solubility increase that we saw with succinic acid. So now most formulations that we prepare as solutions, we need to look at excipients which will help with the solubility. And these are two excipients as an example that help with the solubility. Now, what happens when we take this compound and give it to rats, and or you test in vitro with the RBCs? So in this case, this is an in vitro test with red blood cells, and we took a formulation that has succinic acid and cyclodextrin, that's shown in red, red diamonds, or the black boxes, black circles that are showing a formulation that has succinic acid, but that does not have cyclodextrin. It has mannitol instead to maintain isotonicity. So when you see a formulation with succinic acid alone, you see a lot of release of hemoglobin, which indicates toxicity to the RPCs. Whereas a formulation with cyclodextrin, you don't see that. It's pretty flat at the bottom. And that's very, very, counterintuitive. You would try to figure out what's happening here. We also see a difference in the plasma concentration time profile in a formulation with and without cyclodextrin. Taking all these data together, what we start to think is there is a role of drug cyclodextrin complexation in such a way that those micelles that are formed, or those self-association structures that are formed in the presence of succinic acid and cyclodextrin, reduce the free fraction of the drug in solution and impact parenteral PK and toxicology. And this is really focused on how strong the interaction is. In our case, we believe that presence of these key excipients increases the strength of interaction. So in this third case study, what we found at a high level is strength of interaction being the key. And in our case, it is really the cyclodextrin molecules. I'm showing the schematic of the structure that's taken from a website, but really these cyclodextrin molecules interact with the drug. And again, for example, here we show water molecules with these red and blue circles, and we show our drug, and we show cyclodextrin. There is interaction happening. But this interaction in our case is significantly enhanced with the presence of uh, the polyanionic buffer. And that polyanionic buffer helps with that increase in interaction. And the strong interaction then has an implication on the free concentration of drug, and that in turn has an implication on the toxicology profile. Now, drug cyclodextrin interaction in IV solution is known, and these interactions, if they are so strong, they will influence in vivo PK, and this is a literature example. The example that I am citing here on our case study, it was not
The
just
way
the
we
drug
understand this
cyclodextrin.
is that the strength of binding is actually the key. So in this case, for example, we have the drug which binds with succinate to make a hemisuccinate complex of the drug. Now, this is not just understanding of or a hypothesis or a theoretical understanding. This has been verified by NMR. We were able to prepare semi-crystalline forms of the hemisuccinate, salt of the drug. So we know that this is real and it happens. And the paper that's cited at the bottom shows, much more detail in terms of experimental data that gives us the confidence that this is actually a real phenomenon. But what happens is when you add another excipient, that's cyclodextrin in this case, you actually have a stronger complex. And this is what I'm showing on the right as an illustration of what happens when you have cyclodextrin combined with the drug and the succinate. You have a micelle that's much stronger and bigger, and there are some data which actually showed that this actually happens. And combine this information with the in vivo data, we see that there is a practical impact of these things in how the drug behaves in a drug product in vivo. So strength of binding is a very important parameter here.
So taking home those messages about the strength of binding, really highlighting the element that you need to understand when that interaction is getting strong enough that it's starting to have an impact on performance. Now, this fourth case study, the final example I have, is where the self-association leads to a phenomenon of precipitation. And this precipitation behavior is when the physical instability in solution becomes manifest. It's a different compound here, different case study, experience over the years working on different compounds. But what you see in this compound is particle size by DLS on the y-axis, and with different excipients, the excipients that are added to the solution formulation on the x-axis. And you see different sizes that we see on the DLS. This is a three-dimensional plot where those blue markings, they are indicative of the size of the peak coming towards the reader or the reviewer in this case. And this is true for several different model APIs shown on the right side. It's not just for one particular compound. So these compounds are known to make aggregates in solution. This aggregation in highly soluble self-associating species is actually very, very common. Now, what happens when we have polyvalent counterions in those solutions? Can they induce more aggregation? And that is what we found here. So for example, citrate buffer versus non-citrate buffer, we can see change in the aggregation behavior over a period of time, and the presence of aggregation behavior in the initial time point when we have non-citrate versus citrate buffer. And these things have practical implications. For example, here I'm showing a picture of two vials where one vial shows significant precipitation, whereas the other vial has a clear solution. And this is what's happening on stability, while both vials have the drug, which is really in its native state. There is no degradation, no chemical change. So it's really a physical instability of the compound. And this physical instability is linked to the buffer species. So polyanionic species such as citrate, you can see the precipitation in the vial, whereas monoanionic species like acetate as a buffer, you do not see that precipitation, and you do not see the precipitation as water. Now, this is a behavior that is difficult to predict, but you can start to get a handle on this kind of behavior if you invest early in understanding what's happening with these interactions. So for example, in our case study, what we are seeing here is on the left, we are showing cooperative hydrogen bonding interactions at low API concentration. and high counterion concentration. This is where the succinate, the citrate, they start to interact with the drug. And this is in equilibrium with the drug self-association on the right side. Now, drug self-association can increase supersaturation, but drug interaction with the excipient can lead to precipitation. Now, really, the game here in the formulation world is to really keep the interaction to the right so that you have more of supersaturation behavior and less of precipitation behavior. And you will achieve that by modulating the concentration of those polyanionic species in solution, ideally avoiding those altogether so that you have the equilibrium shifted to the right. So this kind of precipitation behavior, even though difficult to observe initially, and it's a stability behavior, it's really driven by what's happening in solution. Again, the take-home message is this schematic I'm showing at the bottom, the self-association versus the complexation behavior, driving supersaturation versus precipitation. Very clearly evident in the last case study, the middle cross that we see here. So as we go home and we look at, how is this work, how is this presentation applicable to our day-to-day work, you want to look out for common underlying themes across the molecules, across the case studies that I showed here. The API is amphiphilic. There is hydrogen bonding and hydrophobic domains in the API that lead to a tendency to self-associate in solution under certain conditions. And those self-association behavior can have an impact. Now you need to modulate self-association versus precipitation by also paying attention to how the excipients are entering this interplay. And with this, I would like to pause here and stop here and open for questions. And I definitely want to acknowledge several colleagues which have been involved in lots of studies that included, the case studies that I showed here, and open to any questions.